is Eugene DePrince from Florida State University. Eugene, are you up? All right, excellent. So Eugene's going to tell us about two-electron reduced density matrix theory, focusing on some of his beautiful recent work in this direction, focusing both on active space aspects of it, as well as how do we get, for example, some non-dynamic correlation on top of that. And so I'm really excited to introduce Eugene, who is a former student from my research group at UChicago, to kick off our second talk here at the conference. Eugene, have you tested the slide? Okay, so everything's—
Yeah, well, good. Now there's way too much stuff up here. Oh no, you can see my JCP stuff. Go away. So, okay. Thank you, David, for very nice introduction. And thanks for the invitation. I'm really happy to be here. This is great. And I'm happy to be the one who extols the benefits of RDM-based methods. I lied a little bit in my abstract, so I'm probably not going to talk about dynamic correlation corrections, but basically we can do all the standard corrections to CASSCF that anyone else would do, such as MCPDFT. Okay. My talk might go long. I should probably start my timer. So I'll go ahead and acknowledge my group now. This is the last in-person picture we had back from May. Florida's beautiful. Everyone should come work with us in Florida. A lot of students contributed to what I'm going to talk about today. Marcus Liebenthal, Rain Lee, a current postdoc, and several former group members, Sina Mustafa-Najad, Alyssa Maridzik, many people. And most of this work was supported by Army Research Office, Small Business Technology Transfer Program. And if you're interested in running any of the codes that I talk about today, I have implementations both in this package. I have to move my face. In this package that I call Hilbert, that's a plugin to Sci4, and they're also implemented in QChem. The QChem code is much faster, but the Sci4 code is free. So there's that. Okay, let's go. Okay, so jumping right in, what I'm going to be talking about today is RDM methods as a replacement for a solver, a wave function-based solver for CASSCF calculations. And so conventional method for describing non-dynamical correlation at zeroth order, we have this complete active space self-consistent field method, which we learned a lot about in the last talk. And in the conventional formulation of this problem, the active space is described by a configuration interaction wave function. And in the event that that's a full CI wave function within the active space, then the number of parameters in the problem blows up exponentially with system size, which is obviously problematic. So the largest CASSCF calculation I know of actually comes from Lara's work that involved a 20-electron, 20 orbital active space. And beyond that, you're just out of luck. So if you want to get beyond this limit, you have to choose some different ansatz for describing the electronic structure of the active space that doesn't blow up exponentially with system size. And so I'm going to talk about using the two-electron reduced density matrix for this problem. The nice thing about two RDM methods is the number of parameters increases only quartically with system size. So out at a 50-50 active space, we'd have something like 10 to the 7 variables versus 10 to the 28 with the exact wave function. I should say, though, that there's many other ways to achieve approximate CASSCF that has more favorable properties than the full CI within the active space. Selected CI, DMRG, semi-stochastic heat bath CI, full CI quantum arc, Monte Carlo, and all these different flavors of approximate CASSCF and ORMAS, which we just heard about as well. Okay, why can we get away with using the 2RDM instead of the wave function? Well, there's a very nice property that for Hamiltonians with only two-body interactions, the electronic energy is exactly expressible in terms of the 2-electron reduced density matrix and the 1-electron reduced density matrix. And we can understand physically what these things mean if we think about the fact that they map onto probability densities. So for example, one RDM maps onto a 1 particle probability. So it tells you where you're likely to find your electrons. I think we all know that. And a 2 RDM maps onto a pair probability density or a conditional probability. So for example, if I had an electron sitting at hydrogen 1 here, what's the probability of finding the other one? Well, most likely to find it at the other hydrogen center. And these electrons should be correlated. So they do this little dance when you move electron 1. Electron 2 will move out of the way. Okay, so armed with these two probability densities, we're able to exactly describe the electronic energy. And as I already argued to you, these are much more compact objects than the n-electron wave function. So it becomes tempting to try to invoke some kind of variational principle whereby we would determine the elements of these RDMs directly by minimizing the energy with respect to variations in them. And that is a fantastic idea and a very old idea, but it comes with a really important caveat, and that's it's very easy to write down a 2 RDM or a 1 RDM that gives you a very low energy, but doesn't actually correspond to a wave function. So that means that 2 RDM is not n representable. It's the language we use. So when doing these calculations, we have to ask ourselves what types of conditions the 2 RDM should satisfy in order to guarantee that it corresponds to an anti-symmetrized n-electron wave function. So here's I'll just take a break and say, I was inspired to give a more pedagogical talk than I was intending during the introduction because I realized what a diverse audience we have here. Anyway, okay, so the formal definition of an ensemble n representable 2 RDM is here. This thing is meaningful if I can obtain it by integrating out all but 2 electrons from an n-electron density matrix. This is a useless definition in practice though, because it requires knowledge of the n-electron wave function. So typically we try to enforce some sort of necessary conditions on the 2 RDM. There's some trivial ones. The matrix must be Hermitian. We have a fixed number of pair of particles, so we should fix the trace of this RDM. We're dealing with fermions, so it should be antisymmetric with respect to swapping labels. And also the least trivial to enforce in practice is the fact that the eigenvalues of this 2 RDM should be non-negative, or it should be positive semi-definite. And that reflects the fact that the eigenvalues are related to probabilities, and probabilities can't be negative. Okay. So at the end of the day, the variational optimization of the 2 RDM ends up being a semi-definite optimization problem because of this last condition. And here's a very incomplete list of references to groups that have achieved just such a procedure. Please don't get mad at me if I didn't include you on here. I admit that it's an incomplete list. Okay, how does this work in practice? If I take a very puny system and calculate the full CI energy in a puny basis set, this is my target. If I do a calculation that enforces exactly the conditions I just described to you, I get complete nonsense. The molecule is not even bound, which is problematic. And far worse, the energy is much lower than the full CI energy. So this immediately tells me that this 2 RDM cannot be n representable because it gives me an energy that's less than the full CI. So that means it can't have a wave function associated with it. So that means there must be other conditions here that we're missing. So just like we can think about a 1 particle probability or a 2 particle probability, we could think about other types of probability densities and keep those positive. So for example, I could consider the simultaneous probability of finding 2 holes instead of 2 electrons and keep that RDM positive semi-definite. And I get a much more reasonable looking potential energy curve. Still qualitatively wrong in the dissociation limit, but at least the molecule is bound. That's something. I could go beyond this and consider pair probability for a particle in a hole. And then at that point, I get a much more reasonable looking curve. There's still some problems in the dissociation limit that we could talk about if anyone's interested. But overall, the shape of the curve is very nice. These conditions are PQG or DQG constraints of Garrett and Perkis that have been known since the 60s. But it's only more recently, starting I guess in the early 2000s, that these calculations started to become actually practical. Okay. Those conditions that I just described to you live inside of a systematically improvable hierarchy of conditions where we could think about 1 particle constraints, 2 particle constraints, partial or full 3 particle constraints. And then if we go up and constrain the n particle density matrix to be positive, then we have something that's equivalent to the full CI. And so we have recovered our original intractable problem. So typically we'll stop at the 2 or 3 particle level where we can have calculations that scale as either the 6th or the 9th power of the system size. So that would be either the number of orbitals in a full space calculation or the number of active orbitals in a CASSCF calculation. Okay, the whole point of all this was that we can do really big active spaces using this type of approach. Here's kind of an old paper, but illustrates this point nicely. I'm calculating here the singlet triplet gap in the linear polyacene series, where the active space consists of the pi network. And with, let's see, a few things to point out here. So the singlet is the lowest energy state here. So the triplet's higher in energy, and out of dissociation, the singlet triplet gap is finite. It's around 8 or 9 kcal per mole. Not dissociation, sorry, the infinite chain limit. Other things to note, just 2 particle n representability conditions in a couple of different basis sets does pretty well relative to DMRG, very similar results. And all of these methods do pretty well relative to experiment for the experimental data that I've included here. And then I should point out this dashed line represents the point beyond which you can't do an exact CASSCF calculation. It's an 1818 active space. And all the way out here at this end, we have a 50-50 active space. Our algorithms use density fitting, so we can optimize a large number of orbitals. So here are almost 2,000 basis functions. So the point is we can treat really big active spaces and we get pretty good results. For this particular problem, other cases will require 3-body constraints. If you care about the performance of such a method, if I tick down the basis set, I can give you reasonable timings. And on actually at this point, pretty old CPU, this is a 3-hour calculation. On a pretty good GPU, I can get this done in under an hour. So that's pretty good, not too bad. Okay, when we have these types of calculations that enable large-scale when we have this approach that enables large-scale CASSCF calculations, we can start to ask interesting qualitative questions about electronic structure in systems that maybe we couldn't describe correctly using something like DFT. So for the next few slides, I'm going to discuss how open shell character of ground states of these polyacene molecules change with either increasing chain length or changes in the edge structure. So I'm going to consider these linear oligoacenes and the circumacenes and periacenes, where the only difference between the circumacenes and the periacenes is this edge structure. And so I can define 3 measures of this polyradical character that give me basically the same result. First, I could just talk about natural orbital occupations, where here an occupation of 2 means an orbital is doubly occupied, 0 means it's empty. So I have more or less MO theory picture for naphthalene, doubly occupied or empty. And then as I go to larger molecules, I start to leak density out of my highest occupied natural orbital and into the lowest unoccupied natural orbital. And then around 9 or 10 acene, I end up with a singlet biradical and much more complicated polyradical character out for the larger members of the series. We see basically the same thing in the circumacenes and periacenes. The onset of polyradical character is very similar for the circumacenes, out around 3,7 circumacene. That's a pretty similar degree of polyradical character to what we have here for just 7 acene. But the periacenes behave very differently. They become polyradicals much more rapidly, and this complicated polyradical character emerges at only, I should say the singlet biradical character emerges all the way by only 3,5 periacene. Okay, periacenes, most severe polyradical character. Oh, I should point out also, this calculation involves a 64-64 active space, and with the GPU, this is only 4 hours, so that's pretty cool. We could also define something called an effectively unpaired electrons, which is just a number defined in terms of natural orbital occupation numbers. And these tell us a pretty similar story. As we go to larger members of the series, we start to build up unpaired electrons along the edges of the molecule. And if you count up the number of unpaired electrons at the edges, you find that the circumacenes and linear oligoacenes have pretty comparable numbers of unpaired electrons, whereas the periacenes have much more. So again, periacenes are displaying the greatest degree of polyradical based on this metric as well. I could look at geometric indicators of this polyradical character, specifically something called bond equalization, which is related to the buildup of unpaired electron density at the edges of the molecule. Here, the way bond equalization is defined, well, first I'll talk about bond length alternation. So as you move across this chain, so here I have 3 acene, 4 acene, 5 acene, 6 acene, and this x-axis represents the carbon bond length position. The bond lengths alternate as you move across the chain. And in black, I have bond lengths for the singlet state, and in red, I have the bond lengths for the triplet state. And you can see this alternation persists up for the larger molecules, but I've defined something that I call a bond equalization. It doesn't matter how it's defined, but that number increases as you go to the larger members of the series. Okay, you can see there's no alternation in the middle of the molecule. This type of behavior persists in the 2-dimensional members of these series. Again, it's the same story. Bond equalization increases with increasing chain length. And again, the linear oligoacenes and the circumacenes have very similar bond equalization, whereas the periacenes live in a completely different category. The bond equalization is much larger, according to this metric I've defined. I'd also like to point out that these bond length alternation patterns for the singlet and the triplet and the periacenes become almost indistinguishable, which kind of supports the idea that you have unpaired electron density building up at the edges of the molecule in both the singlet and the triplet state, and that leads to the same geometric distortions. And last time I gave this talk in front of my colleagues, it was pointed out to me that this looks like a cat, so there's a picture of a cat. Okay. As I mentioned, all of the calculations I just described to you were done using these two-body constraints, but not all problems are well described by just these two-body constraints, so sometimes you need to go up to higher order constraints, including these three-particle constraints. So I'll just show you here. If you wanted to enforce full three-particle and representability conditions, that would require, that would involve maintaining the non-negativity of the eigenvalues of 4 different reduced density matrices: a 3-particle RDM, a 3-hole RDM, 2-particle 1-hole, and 1-particle 2-hole RDMs. And also this 3-particle RDM needs to contract correctly to the 2 RDM. So all of these things need to be true in order for the full 3-particle positivity conditions to be satisfied. You could also define a subset of conditions that are partial 3-particle conditions that are based on the fact that the sum of any 2 positive semi-definite matrices should also be positive semi-definite. So we can define T1 and T2 here. That should be, their non-negativity is implied by the non-negativity of these other RDMs. And the nice thing about the T1 and T2 conditions is the 3 RDM exactly cancels on the right-hand side. So you only have expressions that depend on 2 body quantities here. Should note that 3-pos implies T1 and T2, and 3-pos will be more accurate. And enforcing any of these 3-body constraints is going to require 9th power floating point operations. The prefactor will be smaller for T1 and T2. Okay, so just to show you how these conditions can clean up energy errors, here's nitrogen dissociation in a big basis set with a 6,6 active space, the exact CI solution, and then the PQG solution. Great looking curve. There's some error in the spin recoupling region that is not that big, but you might not be satisfied with a 20 millihartz error. Well, you can just toss on some partial 3 positivity conditions, and then your maximum error is more like 5 millihartz. So general rule of thumb is when RDM methods work, 2-particle conditions can give you qualitative accuracy, and 3-particle conditions often will give you quantitative accuracy. Okay, so very recently, we started thinking about just how accurate 3-pos can be in some very challenging systems. There's a great paper from Francesco Evangelisto's group from last year, where they explored a bunch of different hydrogen cluster geometries as a strong correlation benchmark. And a lot of times people will just think about this linear chain of hydrogen atoms, but it turns out you can enter very different correlation regimes if you consider these 2- and 3-dimensional structures. So in this paper, they explored a whole bunch of methods, and here's the chain and the ring. Not surprisingly, Hartree-Fock fails, second-order perturbation theory fails, couple cluster fails, everything fails, except for RDM methods. Even just with 2-body constraints, the errors are pretty good here, and the reason that this, the fact that this curve is parallel to 0 means that the shape of the curve is very good at the 2-body level. With 3-particle conditions, at least partial 3-particle conditions, the method really nails this problem. So that's great. And it's basically the same story for the 1D ring problem. 3-particle constraints give you very accurate results. What was very surprising to me is that if you go to these 2- and 3-dimensional structures, number one, 2-particle constraints lead to huge errors. These are on the order of 100 millihartz here, almost 200 millihartz, which is definitely not acceptable. And even partial 3-particle constraints lead to pretty large errors. I think these are 30 or 40 millihartz, if I remember correctly, at their largest. So obviously, this is interesting that these methods don't perform nearly as well as I would have expected. And we decided to try to see what full 3-particle conditions would do for this problem. The chain and the ring structure, these are the easy ones where T2 condition was doing quite well anyway. That's the orange curve. My blue curve for 3-pos is really very accurate. Error is much less than a millihartz at all bond lengths. Same thing for the 1D chain, the 1D ring. Maximum errors are around 2 millihartz, so that's pretty awesome. But then again, the sheet and the pyramid geometries are much more difficult to describe. And so here I'll just note that I stopped calculating, my postdoc Rain stopped calculating these curves at around 1.5 angstroms because there's a state crossing in the full CI that complicates the analysis. But anyway, the point is 3-pos does clean up the errors from the T2 conditions, but not nearly as much as we would have expected. So we started to try to ask ourselves, what is the reason that three particle conditions are kind of failing here? I say failing, I'm really being overly critical because these errors are really quite small compared to the errors that some other single reference methods give you in this regime. Nonetheless, I'd still like to know what is the source of these large errors. So we started to think about what types of correlation metrics might correlate well with the errors that we're seeing. And so we looked at von Neumann entropy, we looked at the magnitude of the two-particle cumulant RDM, that's the part of the 2-RDM that corresponds to pure two-body correlations. We looked at the magnitude of the 3-particle cumulant and the ratio of those two. So this would be like the importance of 3-body correlations, and this would be the relative importance of 3- and 2-body correlations. And first, I'll put up these errors again. The entropy does not correlate well with the errors we see in 3-pos. So these all increase monotonically with this chain length, the bond length for all system sizes, which is not the behavior we see. There's a maximum in these curves. Same thing, with the exception of the pyramid geometry, we see the same thing for the 2-cumulant magnitude. These increase monotonically, whereas our errors don't. The 3-particle cumulants have a very fundamentally qualitatively different behavior. The magnitudes have some maximum or plateau at some geometry, so they don't monotonically increase. And then if we look at the ratio of these two, then the maxima in these curves, again, this can be interpreted as a relative importance of 3- and 2-body correlations. The maximum in this curve actually corresponds quite well to the maximum in the error for the 1D chain and 1D ring. And the maxima in the pyramid and sheet geometries, well, there is no maximum in the pyramid geometry, but in the sheet geometry, this maximum corresponds pretty well with this one. So we hypothesized that maybe 3-pos has some difficulties when 3-particle conditions, 3-particle correlations become very important. Tends to over-correlate the 3-particle conditions in these cases. However, this correlation is okay for these systems, but tests on other molecular systems reveal that this really isn't a universal indicator for the reliability of this method. So in this case, correlation is not causation. And then I want to point out again, I'm being very critical of 3-pos, but it's much more accurate than the single reference approaches to this problem. Okay. All right, these calculations are extremely expensive and often impractical because of this high scaling, and there's also a high prefactor associated with these methods. Fortunately, we have explored GPU performance of these methods, and the performance ratio is much better than what we see in the case of the 2-particle conditions, which was only less than a 4x speed up. So here I have some very preliminary timings from my student Marcus and postdoc Rain for these linear polyacenes, looking at just benzene, naphthalene, anthracene, and tetracene. And we can see that even for benzene, the GPU is slightly faster. And then at anthracene here, the GPU calculation is more than an order of magnitude faster than the CPU-based calculation. So if this is a 1414 active space, that takes about 6 hours, which is still pretty slow. So these are very expensive methods, but nonetheless, the GPU calculation is 11 times faster than the CPU one. Out at tetracene, this is an 1818 active space. This is kind of disappointingly slow. It takes about 3 days for this calculation, but there's, in my opinion, a lot of room for improvement. I won't get into details because we haven't finished this paper yet, but there's a lot of room for improvement here. Okay, I think I've only talked for 20 minutes, so I'm going to talk a little bit about excited states in the context of V2RDM theory. Which is a very sad story, and I'm trying to stimulate discussion here. So sad story of excited state V2RDM theory. And very obvious, everything I've talked about so far has been state-specific V2RDM based CASSCF calculations. And even more than just state-specific for the lowest energy state of a given spin symmetry. Okay, so we can only get ground states. So an obvious goal would be to be able to describe electronic excited states, not just for excitation, for many reasons. But there's an immediate obvious problem, and that's that these V2RDM methods can only treat ground states. So if you recall, we're minimizing this energy functional where D2 and D1 are defined in this way. And there's two major problems. One, well, at least I don't know them. We lack constraints to differentiate ground and general excited state RDMs. And also, we lack any symmetry information because these are basically the square of the wave function, which means we've washed out all spatial symmetry. So in a wave function method, you can do a ground state calculation and get out several different states of different symmetries if your molecule has a high symmetry. That's not the case in these RDM methods because the symmetry information is completely gone. So unless we have some operator that we can constrain like spin, we're stuck with only one state that we could get out with these calculations. Okay, so we've tried many different strategies. This is so old, I'm not even gonna talk about it. We tried some frequency domain methods. There's something called an extended random phase approximation, which is similar to some linear response methods that David has developed. There are problems with these methods though. Number one, it's a single electron theory and it's not particularly accurate. Number two, there are some real challenges with describing excitations out of degenerate states, and that's related to a problem of pure state unrepresentability that I probably don't have time to talk about. But there's a pleasant surprise here. These methods form a basis for a family of dynamic correlation corrections to V2RDM CASSCF based on the multi-reference adiabatic connection that Kasia Pernal has developed. So we applied that approach to our V2RDM CASSCF in this paper. Okay, the strategy I'm going to talk about in detail for the next 5 minutes is the imposition of orbital angular momentum constraints. So I mentioned that if I don't have any operators that I could constrain to differentiate states, I can't differentiate different excited states. But for atomic and linear molecular systems, we can distinguish between different states based on their orbital angular momentum symmetry. So here's the form of this operator that everyone knows. The thing I'll point out to you is there's an I here. So if I want to evaluate the expectation value of LZ, and I want to get a value of LZ that's anything but 0, I need an RDM that's complex valued. So in order to explore these types of symmetries and look at non-zero Z projections of the orbital angular momentum, we have a technical challenge that we need to treat complex valued RDMs. That's fine. Postdoc Rain Lee did some great work and implemented a complex valued version of V2RDM for us to play around with. Moreover, in addition to the fact that we could only describe zero valued angular momentum projection states with a real valued V2RDM code, real valued V2RDM describes some states very, very poorly. So if I'm looking at the singlet triplet gap in a pretty simple molecule, O2, I get some surprising results. If I just compare to experiment, here's experimental energy in EV, high level of theory versus real valued V2RDM in a puny basis set, results are reasonable. If I go to a larger basis set, double zeta basis set, expensive method still does quite well. V2RDM method gives a singlet triplet gap that's half of what it was in the small basis set. So that's a little bit problematic. Moreover, if I go to an even larger basis set, then the sign on the singlet triplet gap changes. So this method is qualitatively wrong for this problem, predicting the singlet triplet gap in O2. How can we fix this? Well, we can use those angular momentum constraints I just mentioned. If I have a complex V2RDM code with angular momentum constraints, then I fix the sign on this. Not only do I fix the sign, but the answer is actually pretty good compared to the higher level of theory. So that's great, we can fix this. One interesting problem we run into though is that not all angular momentum projection states are treated equally by these V2RDM methods. So if I take a carbon atom and constrain angular momentum for this triplet P state, I have two different curves here. So green is the full CI solution. Blue and red are V2RDM with PQG conditions, enforcing either just the expectation value of LZ or the, so that should be equal to 1. I'm sorry, -1, 0, or 1, or the variance on LZ, making the variance on LZ 0, which should be true for an eigenfunction of this operator. So first of all, just constraining the expectation value of LZ, I see I get very different results depending on the projection I choose. I get much more reasonable results if I constrain the variance as well, but these still aren't exactly degenerate, which is problematic. And this problem isn't limited to this case of triplet carbon P. It also is a problem for singlet D state. I have 5 different states with 3 different energies. In both cases, the maximal angular momentum projection states are the most well constrained. And then this problem persists for other atoms. It's exactly the same story. There's no reason to talk about that. This is actually a problem that others have observed before in the case of spin angular momentum, SC. So there's this great paper that explores basically this problem, but just for spin angular momentum. And they come to some similar conclusions that the maximal spin projection states are always the ones that are the best constrained, and it's the non-maximal ones that are problematic. Okay, so at the end of the day, we can compute a limited, in limited classes of systems, we can calculate excited states using these angular momentum projection constraints. But there are problems. We could go on. Ultimately, we actually started working on these methods because we were interested in developing a relativistic version of V2 RDM CASSCF, and we wanted to look at total angular momentum projection states. So we can explore this in the non-relativistic limit, and that can tell us whether or not this is even a worthwhile pursuit. Because if I can't describe the non-relativistic limit correctly, what's the point in adding spin-orbit coupling? Okay, so I'm going to look at several different terms for just a carbon atom. So for triplet P, there's 3 different J states, 0, 1, 2. And I see this completely insane behavior that's not at all surprising based on the results on the previous slide. So all 3 of these states should be degenerate, and each of the M sub J states for each J should all be degenerate. So I should have 9 degenerate states here, and I don't get anything looking like 9 degenerate states. Each J value has basically its own energy. And then within a given J value, different M sub J states have different energies. Here, this is enforcing variance constraints or not enforcing variance constraints. So in the case of this J equals 2 state, the variance is very important in these guys, but it doesn't really help us at all for the M sub J equals 0 state. So in my opinion, this is a very sad, well, it's interesting, but it's very sad because to me, this is kind of the nail in the coffin for any hope of treating relativistic effects with these types of approaches, because I cannot even come close to describing the non-relativistic limit correctly until we discover additional constraints that can fix this problem. Okay, I think I was supposed to talk for 30 minutes, so I'm going to skip all this other stuff. I had 8,000 slides on pure state constraints. We'll just skip that. And I'll get to my conclusions. Wow, that's a lot of equations. Okay, take home message. V2 RDM approach is one of many strategies to enable large-scale CASSCF calculations, but we can only really achieve state-specific calculations, lowest energy of a given spin state symmetry. What I didn't talk about today is the fact that we can easily add dynamic correlation. Laura mentioned this briefly. We can use a method like our MCPDFT to just tack on dynamic correlation. And the fantastic thing about MCPDFT is it's free. You spend all your work getting your nice RDMs, and then you get the dynamic correlation basically for free. And then there's also this multi-reference adiabatic connection that's based on extended random phase approximation. This comes from Kasha-Fernall's work. And then the last point is that excited states are hard. And here's the thing to stimulate discussion. Without some breakthrough, I think that we should just stick to wave function-based methods for describing excited states, because I don't see a reasonable path forward for V2 RDM methods without some breakthrough in terms of constraints that differentiate ground and excited states. So with that, I'll throw up my acknowledgements one more time and thank my students that contribute to this: Marcus, Rain, Sina, Elvis, Wayne, Jacob, a lot of them. And of course, thank you to funding agencies. And then I'll take any questions if you guys have them.
All right, excellent. So let's actually go ahead and unmute ourselves here and give a round of applause for Eugene's talk. Okay, so go ahead and the live applause. Awesome. All right, so we have some time to open the floor for some questions before we move on to third talk. So let me start off with Paul Johnson. Would you like to give your question? Sure, go ahead.
Thank you very much for your talk, Eugene. So for excited states, dumb question, and you'll tell me it's wrong. Can you not access them indirectly by evaluating excitation energies with, say, double commutators? Like minimize the expectation value of a double commutator with a Hamiltonian with your two-body density matrix.
So like a kind of, well, so first the ERPA, well, that's different. You could impose like variance constraints. I think, is this what you're describing? So,
yeah, so not exactly. Like your Hamiltonian should be invariant to one-body unitary transformations. So when you evaluate the expectation value of single commutator with the Hamiltonian with your wave function or density matrix, it should be 0.
Yes.
With respect to two-body unitary transformations, it should be positive definite or positive semi-definite, I don't know. And
Yes.
the eigenvalues, I understand, correspond to excitation energies, but I could be wrong. So if you...
I don't know. I've never tried this. I don't know if
okay.
Dave has tried anything like this. Is
Yeah,
this...
so you can basically, I think it's kind of related. So Paul's kind of talking about essentially what we call the excited state or excited spectra 2 RDM method or a Hermitian operator method. So one can basically use two-body operators or one-body operators and use these commutators, and then you can just solve for the manifold of excited states. So there are, so basically that's one way to do it. Another way to do excited states is also to take the contracted Schrodinger. And so in a lot of our work, we'll go ahead and solve the anti-Hermitian contracted Schrodinger equation, which, like Paul's suggestion, has commutators in there and is sort of effectively doing that type of process too. So one can extract, very accurate excited states to about, less than a millihartz of accuracy by solving contracted Schrodinger. So while it is true the variational 2-RDM has challenges for excited states, there are ways around it by essentially using, single and double commutators, or even for higher commutators through something like the ACSE type contracted Schrodinger framework.
So now that I understand what you're asking more, that's basically the same thing that happens in the ERPA. You build this double commutator matrix and diagonalize it.
Yeah, okay.
But those are just, there's only singles there. I mean, you could build the same double commutator with doubles as well, but then it'd be much more expensive. The nice thing about with just singles is the matrix only depends on the 2-RDM.
But even like pair attachment and pair removal, you can do.
Yeah, you could do the same
which
thing.
Would be like, yeah, that's particle RBA. Yeah, forget it. Thanks.
Good question. Peter?
Yeah, nice talk, Eugene. If you want to track the LZ quantum number in a linear molecule, another way to go is to calculate only real states. Of course, then the pi x state is not an eigenfunction of LZ, but it is an eigenfunction of LZ squared. So that's then a two-electron property, which you can use your two-particle reducing density matrix to assess whether you've got an eigenfunction of. I wonder whether the reduced density matrix functional thing that you've been describing is invariant to that rotation between the pi x, pi y, pi plus, and pi minus states, and whether that's related to the difficulty you seem to be having in the carbon atom.
Well, I can't tell a difference between the pi x and pi y states because there's all that symmetry.
They're different to pi plus and pi minus because if you had pi x, you'd have a real
right. So if I constrained LZ squared and got a pi x or pi y type state, it would be some linear combination of those two. It would be an ensemble state. And I can't tell the difference between them without any other operators to constrain.
So would you get the same numbers as doing RDM theory on just the pi plus state, which is what you described?
I don't know the answer to that. I would suspect that it would be similar, if not the same.
Okay, thank you.
Because I guess I could always take linear combinations of my +1 and -1 states to generate a PX state.
Because the energy functional is linear,
yeah,
but the constraints are not. That's kind of what I'm trying to probe and understand a bit.
No, the constraints are all linear.
So are you saying you can prove that the energy, you get the same energy? Should get the same energy?
Right, the energy should be invariant to those changes. So if you take different combinations, the energy, well, I see what you're saying. That's a good question, actually. So yeah, there could be variations actually in that. And I think that comes down to sort of where one's pinning oneself on the manifold of angular momentum states to some extent. So there could be variations.
I want to make a comment. I calculated these calculations on atoms and constraining, for example, SX states or SY states. And it turns out the SX state and SY state have the same energy. So I believe if you do a linear combination of them, they would probably still be the same.
Oh, okay, so in those cases, you're seeing the same flat energy with respect to either state. Okay.
Yes, I don't remember if I did it for orbital angular momentum. I probably did. I can't be sure, but I'm pretty sure I did SX and SY.
So does that mean that all the trouble in the carbon atom is about spin, not about the orbital angular momentum?
No, because it shows up in the singlet D state, for example. And so there's only one spin state.
Yeah, okay, thank you.
Laura, question?
So concerning the molecular calculations, if I understand correctly, if they, I mean, if you look at several electronic states that belong to different erupts, you can do that, right? You could compare different singlets belonging to different erupts.
No, because the point group operator is an n-electron operator.
I see. So you cannot exploit point group singlet, right?
No. Well, I mean, we can use it to make a calculation faster, but I can't exploit it.
But to compute excited states as states belonging to different erupts.
Yeah.
No, I wanted to ask about when you show the singlet triplet gap, I wanted to know what about the singlet, but you cannot do that, right?
Mm-hmm.
Yeah.
Correct.
Okay. All right.
Yeah, David, just quick question.
Sorry. A question? Sure, go ahead.
Yeah, just to clarify, I mean, what about the traditional approach? So after you find the ground state, you form new projection operator and add it as a penalty term to eliminate the ground state from the search. So you go to the first excited state.
Add what as a penalty term? I'm sorry.
The penalty term will be the projection to eliminate the ground state. Once you found the ground state, you form the projection, which is the constraint now, and you have a penalty term which allow to eliminate the ground state from the search.
But with just RDMs, you can't tell the difference between two RDMs for two different states. The simplest example I could give you is for H2 in a minimal basis, the first two singlet states are both diagonal. They just have different numbers on the diagonal. I don't know how to tell the difference between those using some kind of projector.
I mean, if I eliminate the ground state, I mean, what will be the next one? What did you obtain? I mean, suppose I run the calculation, what should get out of this calculation if I project out the ground state?
That's the thing. I don't think you can project out the ground state when you're dealing with just RDMs. David looks like he wants to say something.
No, I'm just saying that, yeah, Sabri is right though. I mean, if one projects it out, then I mean, formally, basically one would end up with the excited state there. But as Eugene is saying, it's difficult, and so it's challenging within at least the current framework. There are some challenges.
David, you can add it as a penalty term where the parameter is larger than the norm of the Hamiltonian. I mean, then you can really get to the second one. I mean, we did it anyway for other calculation. It looks like if you choose the penalty term in a way that over the range of the spectrum of the Hamiltonian, you can go to the excited state.
Right, because the recent work with Sejan, essentially, that you're doing with machine learning, right? So we should talk about that. We should talk about that. That sounds interesting. All right. Let's thank Eugene again for an awesome talk here. And
thanks for having me.
All right, so we're going to move on to our third